chiefly in mind here. Two are coming from last time. I wanted to say just a little more about this neat theorem of max flow min cut. This was an example of duality, and a particularly nice one. And chapter 7 of the book has examples and more discussion of that. Then you were kind enough to get involved in my new interest, which was, well, the specific question was, when can I complete a matrix given some of its entries? When can I finish it out to have rank 1? And I have some news. So, of course, I'm eager to tell you about it. And then I realized that it might be a pleasure to talk about game theory as another two-person game theory created by von Neumann. And it's another example of duality, but just coming from somewhere, from such a different source that it wasn't recognized for a little while, that it fit the framework. Okay, with max flow min cut, I just have this example to mention. Suppose all the capacities are 1 on the edges. So on every edge we can send 1 unit. How, well, in this example, let's say, how much could I get from the source to the sink? Well, along those edges. Okay. Oh, have I made it so I could get 4? Could I get 4 through on that? Yes, I think I could. Right, because, yeah, so let me make it a little harder. Let me add another edge there. So hopefully I could get more through, but I think I can't. I think that how much could I now get through from the source to the sink? There are 1, 2, 3, 4, 5 edges leaving the sink, and then they go different places. And there could be, as we had last time, the bottleneck could be in the middle of the path, or it could be right here at the sink. Maybe it is. Maybe in this case I can only get 4. I could even I think maybe the maximal capacity is 4. Agreed? Yeah. And the cut that shows me, that proves it, is actually, well, in this case, sort of a degenerate case, the sink is all by himself in the cut. So there's a cut of 1, 2, 3, and 4 edges getting through, and that's the maximum flow also. And let me draw the paths that it could follow, one set of paths that it could follow. Let's see, I could send 1 along this path, and I could send 1 along this path, and 1 around here, and 1 around straight through there. So notice that those paths are disjoint, separate paths. And they have to be, right? With this kind of flow, I'm not going to gain anything by sharing, by sharing an edge with 2 flows. So what I'm trying to say is that for this example, the max flow equal min cut can be expressed in a different way. So what I want to do is restate this for the special case here as the maximum number of disjoint paths S to S prime, source to sink. So there's an example. 4 disjoint paths is equal to what? So I'm looking for how many independent paths go from here to here. And it's equal to this, the capacity across the cut. And I would like to find a different set of words for that. So what happened, this cut, suppose I actually make such a cut. So I'll actually use the eraser to cut the network. So what does a cut mean? It's a separation of the nodes into one group with the source and another group with a sink. Well, sorry that in this example, the group with a sink is only the sink. But nevertheless, that's a cut. And what has that cut done? That cut has separated the source from the sink. It's literally cut the two apart. So the capacity, of course, is across the cut is the number of times we clipped an edge. So here's what I'm trying to say. The maximum number of disjoint paths, that measured how much flow we could do, equals the minimum number of cut edges to split. May I use a strong verb there? To split S from S prime. The minimum number of edges that it took to separate this from this. Do you see that this is a restatement, and maybe we could think why? Why? I mean, this is, as usual, we should see weak duality. So what did weak duality mean? Weak duality, which was usually the easy thing to see. So if I just suppose I had just made this statement, that I draw a network, and I look at how many separate paths there are that don't share any edges. That's what disjoint means, from source to sink. How many paths? And I looked at the minimum number of edges of cuts that I had to make to separate the two. Now, weak should be maximum less or equal minimum should be easy. And remember, it's slightly strange that it's that direction that's easy. Of course, it's the maximum of one thing and the minimum of another. Why is that easy? How do I know that that if I have the minimum number of edges if I find some edges that split, yeah. How do I know that if I find any cut, any bunch of edges I could snip through that would separate source from sink, and I count those edges and I get K, how do I know that the number of paths can't be more than K?
Each edge has to be part of one of the disjoint.
Yeah. Exactly. If each edge, if I manage to cut the thing with K, then there couldn't be more than K disjoint paths, because then I wouldn't have cut one of them. Let me say that again. I'm just sort of easy. Suppose K cuts split S from S prime. Then can't be greater than K disjoint paths. Because if there were more than K disjoint paths, then I didn't cut them all. And then I haven't separated the source from the sink. So that would be the reasoning, that I take any cut that works. I say, okay, maybe it took K separate edges to clip. But then the number of disjoint paths couldn't be larger than k, because then if it were, one of those paths isn't getting cut, and we haven't separated S from S prime. So that says that any cut that's acceptable is at least as large as any count of disjoint paths. So we increase the count of disjoint paths up to its maximum. We decrease the number of cuts to do the best cutting we can, and we have less or equal. And the point is, we actually have equal. And maybe here's a proof of equal. Suppose we have, well, the idea of the proof is that suppose we have a maximum flow. Yeah, this is in the book, and it's hard to take in verbally. But if we had a maximum flow, suppose we had the flow as large as possible, then I want to see why some cut of that size is holding us up. So we have a flow as big as possible. Then I keep with S some edges some with S, some edges I might be able to send more to. Along some edges I might be able to send more. For example, along that edge I could send more. That's interesting. Okay, now I may find another cut here. So I group with the S all the nodes to which I could still send one more. Okay, let me see. I'll use this. So with S, I keep this node because I could still send one more to that. And then, oh yeah, this is going to be tricky because I could now send backwards on this edge. So having sent these forward, I could send one backwards. I think I'm not going to get into this because I don't want the whole lecture to be this rather specific topic. What I wanted, my point is that we have these special dualities for some special network problems, and that they are special cases of linear programming. I mean, what are the equations? Now, so here is one final question on this. What are the equations that govern a flow? I'm trying to maximize a flow. What are the equations that govern a flow? I want to fit it into linear programming. I want to maximize the flow. So I have my unknowns are the flow along every edge. Then I have some inequalities and I have some equations. And if you tell me what those, what describes an okay flow? To match linear programming, I want to ask you what are the inequalities for a flow? So I'll maximize a flow. What are the inequalities? And what are the equations? A flow is what are the unknowns here? The unknowns are, let me say what the unknowns are. Xij is the flow from I to j. Okay. So do you remember that in linear programming you're maximizing something, but you have certain inequalities? Now, what were the inequalities in this flow problem? The inequalities were that the flow couldn't exceed the capacity. We put a capacity of 5, 7, 9, 1, whatever on those edges. So on every edge there was a upper bound, and now I want to say what are the equations that flows have to satisfy? What's the equation? I claim that at every node we've got an equation. At every interior node, every node other than S and S prime, I have an equation, and what is it? It's Kirchhoff's law, right? Kirchhoff's law. So we have the equations are Kirchhoff's current law. That's my little point. That we're coming around again to the most fundamental equation in applied mathematics. I guess I dare say that.
If you're using Kirchhoff's current law, then you have to allow negative flows. How does that change your...
Well, let's see. So I'm interpreting Kirchhoff's current law as at every node the flow in equals the flow out. You're right. So there'll be some pluses and minuses.
Doesn't that change your inequality? So now you have a nonlinear inequality. The magnitude of xij has to be less than cij.
Well, I'll just, I'm not even sure in this instance, but suppose we had what looks like a nonlinear inequality. Turn it into linear inequalities. That's a very good example of how flexible this is. How could I turn that, which certainly looks nonlinear, into linear inequalities? I could double the number, right. I could leave it as xij and add to that minus xij is, what would it be? Greater than, or I've forgotten, minus cij. What would it be? If I want xij to be small, maybe it would be that, would it? Right. And then so, or is that, no? Is it? Is that right?
I think you need to...
I don't get rid of that minus.
No,
On C, maybe. Minus xij greater or equal cij. Yeah, okay. My point is we could do it, and we'd still have linear programming, double the number of constraints, but we'll handle those. And the point I wanted to make was this key equation, Kirchhoff's current law. I don't mean to say that when we look at all of applied mathematics, Kirchhoff's current law jumps out uniquely, except what jumps out is balance equations, conservation equations, in equals out, plus possible sources. That's so much of applied mathematics is, that's one of the equations to look for. Then there'll be the equation that describes the particular the physics of the problem. You know, what is the flow? How does the flow connect to potentials or something? But that balance equation is always there. Okay, so that's I'm going to stop there with the hope. Well, with the hope that you find some of those special cases appealing, and then also with the hope that you'll enjoy game theory. But I'm really keen to tell you about, if you'll help me again, as you did last week, you kept me going through this question. Let me remind you what that question was. The question was, let me put the question here. The question was, I have a matrix, and I'm wondering about which positions could I give arbitrary values and then complete the matrix to have rank 1. So this is so I'm giving any non-zero values, and let's take an example. Let me take the example that I had last time. Well, let me take this example. Could I give any non-zero values in those 6 places and aim for complete to rank 1? Is that possible? And your answer is no, because we have here, if rank 1 will mean, what will rank 1 mean? It'll mean that all 2 by 2 determinants are 0. And that won't be true here. So I better take one of those out there. Or let me make it a little less obvious by taking that one out. Could I now complete? So now I'm less ambitious. I'm putting in 5 entries, and I'm putting them in this position. And could I now complete this to rank 1? And the answer is yes. Right. I could. This 2 by 2 would now tell me what that number had to be. This 2 by 2 would tell me what this number had to be. If I do it this 2 by 2 would tell me that number. This 2 by 2 would tell me that number. Well, and you might say, wait a minute, this 2 by 2 told me that number also. So maybe it's less. Maybe it's it needs a little bit more thinking. So, right, the way I did it was not completely convincing. Because I would have said, okay, do that one, then do that one, then do that one, then do this one. And then you say, wait a minute, those 3 were specified, that determined that one. So I would need a more convincing. What would be more convincing? Can you give me a correct, a better, well, I could go back to that and do it more carefully. But how do you see that could be completed to rank 1? Rank 1 will mean that every row is a multiple of every other row. So, right. We see that row already set.
Yeah, just enough for each row.
Not too many, right. Yeah, that's right. We want to know that just enough and not too many. Okay, so after playing around with examples like that, the conjecture was that the right number to specify, if this is k by k, complete a k by k, so 3 by 3 in this instance, the right number is 5. That's our guess. And so the general guess was 2k minus 1. So that's what I want to prove. That's what I want to prove. That would be the theorem. That it's completion, rank 1 completion is possible if and only if every, and I have to check the submatrices too, every submatrix of let's say, of order, let me call its order k, has less than or equal to 2k minus 1 specified entries. Specified entries. And I'm going to specify them non-zeros. So that's like, I hope, a new theorem. It sort of partly happened because the examples that we played with. So why? So does this example pass that test? Yes. Moved it over to where? Here? As it is. Yes, but of course when I complete it, I can hopefully get it to have rank 1. And as you say, if I looked at eigenvalues, they would be 0 and 0 and whatever that trace is. Yeah, so. Yeah. I put in numbers. So let me take a specific case. Could I give, and you'll see by the way I write these numbers in, 1, 4, 7, 2, and 11. Now the question is, can I complete that matrix to rank 1? Yeah, this is very, thank you for every question you ask. It improves the way I think about it. So So, okay, so we would say, yep, we can do it. All right, I could do it 2 by 2. You know, I would see, okay, what do I need there? I need a half, is that right? And really what I need is that for that row 147, for this row to be half as much, so this would be 7 halves. And for this row should be in the ratio 11 to 7 or whatever. Yeah, sorry. When I said arbitrary numbers, I didn't mean that arbitrary. Yeah, but anyway, I could do it. And you realize why, just to be sure, that I can't do it for any 5. Suppose I specify those 5. Now I can't complete to rank 1 because I'm lost at the start here. If I've made those arbitrary, then that's a 2 by 2 that isn't determinant, that isn't 0, and no way I can fix it. I could make those numbers if you wanted, right? So that's why I have to, in the test, has to go not only the big guy, but all the smaller ones. Because if a smaller one fails my test, the bigger one might still have only 2k minus 1, 5 specified entries here. But the smaller, if a smaller one messes up, then it sinks me before I can, I've got no way to save it. Okay. So let me take a 4 by 4. So 4 by 4, I should be allowed 7 entries. And okay, now here, think through, suppose I have 7 entries. How can I complete? How can I prove that I can complete? So I'm asking, what I'm really talking about now is that math step from doing a bunch of examples and getting convinced and getting a proof that's absolutely convincing. See what I'm trying to say? That I now have to think 7 entries, any 7, subject to this constraint. How can I show that it's possible? All right. So actually, strictly in this proof, I have 2 directions to go, but let me suppose that this test is passed, and I have a 4 by 4 with 7 entries that passes that test, and I'll conclude that I can complete. And then there will be another step of the proof that shows that that condition is necessary. But let's do the first one way. Yeah, okay, I've got 7 entries in a 4 by 4. 4 by 4. 7 entries. Okay. And now let's see. So here's my reasoning. One row has to have, and all the rows couldn't have 2 entries, right? That would make 8. So one row has to have no entries or 1. Okay, see, I'm covering all cases. So one row has to have either no entries or 1 entry, right? So we can reorder the rows and make it the first row. In fact, then we could reorder the columns and make it the first column. So here's so up in the first row is only 1 entry, and I'll reorder the columns. That won't change anything, just to keep our we're looking like that, right? There has to be a row with only 1 entry, because there's only 7 entries altogether, and 4 rows. Okay. There has to be a row either with 1 or there could be a row of all zeros. What do I mean by this, 0? I mean unspecified. Should I put U for unspecified? Okay, U for unspecified. Or I could possibly have I could have 7 in the whole thing, but there would be, let's kill this possibility first here. Okay, now how could I show? Now I've got 7, the 7 are still specified, but they're only in 3 rows. Okay, so what do you think now? Let's see. Well, I've got 4 columns here. Now, the wonderful thing about linear algebra is the relation of the rows to columns. That's what you got to keep remembering. Okay, so I still have 4 columns, and I've got 7 specified. So again, I have a column that has only one or none, right? Because there were 4 columns. I've got to put 7 x's in here. Some column is only going to have like 1 x. And the other 6 are going to be in here. Okay. So I claim that this totally that this can't happen because I'm assuming this, right? I'm assuming this. Let's get the logic straight. I'm proving that if this is true, I assume it's true, and then show this. Show this. This is the direction I'm going. Okay. So I assume that not only the big matrix, the 4x4, had 7 non-zeros, but every submatrix of order k didn't have more than 2k minus 1. But here I have a submatrix, it's 3x3, and it's got 6. So that couldn't have happened. Let me come back to here. Again, I'm going to go the same way here. Now, what do I want to do? I'd like to, okay, now I have one specified guy. That's more reasonable. Unspecified, unspecified. Now I look at the columns. Okay, I've got 4 columns. So what's possible here? This column might have 2 guys. It might have this specified and 1 more. And unspecified, unspecified, right? That could be. Or I better have another or out here. Let's see. So I'm starting with these. Let's see, what are the other... Well, let me follow this case through first. Suppose this is my situation. Remember, I figured out, okay, 1 row does have to look like that.
Well, don't you have to have 2 at each point where you're reducing the matrix?
Well, that's what I have to show, and this is... So in this is the good case where I do. All right, now what's the deal here? I have, it looks like this. And then how many are specified in here? The remaining 5. So what's up with this case? I apply the theorem for smaller size, and I know I can complete this. I can complete the 5 because it's satisfied. All its little submatrices, of course, were part of the assume, and it's got 5, which is the right number, so I can complete it. So somehow I do complete it. Now, of course, I have to just check having completed this to have rank 1. Can I now finish the job? So now, how do I finish the job here? Knowing that those rows are all in the same direction. Those 3 rows are multiples of each other in the small one. Now I have to achieve that in the 4x4. Okay, well, I guess I see 1 row completely set. And so now how do I fill in this row? Just the ratio, whatever. I mean, that row's set. This guy sets the ratio, and I can fill it in. And how do I fill that one in? Again, this was in a certain ratio with this one, so the last entry has to stay in the same ratio. And similarly here, this was in a ratio with this because this was rank 1 in the 3x3, and then when I'm given that, I'm given that. So actually, there's a unique way to finish. So you could say, yep, that was... Now, anybody see that I've got one more case to worry about? Well, this was X, U, U. And then I said, okay, what if my row... What if this column has... let's see. Yeah, right, that's a case I have to worry about. What if nothing else was specified there? Why am I... How do I know that that couldn't be?
Because as
Because then I've got 6 more in the 3 by 3, which I assumed I didn't have. Okay. Now what? Okay, I think I've got another case to worry about. Mathematicians are awful worriers. All right. What else do I have to think of? Maybe what if this had more? Like 3 or 4. Now, how do I deal with that case? What I'm hoping for is to find a 3 by 3 that's okay. Now, what's up here in this case?
One of those other columns.
So one of those other columns will only have 1. Right. One of those other columns will only have 1 because I've used up 3. There's 4 more to specify and 3 columns. So some other column has got 1 easily. Right. Okay. So suppose another column only has 1. All right. Now what? Now the good columns to look at are this row and that column. This row and that column. I'll move that column over. Or you see, out of this row and that column I've used 2, so I'm remaining with a 3 by 3. I have a 3 by 3 remaining with 5. You see that if I look at this remaining 3 by 3, because this row and column have only specified 2, I have 5 unspecified ones in this 3 by 3. I can complete those by induction, is that right? Yep. Right, because whatever, some of those were specified, but a total of 5 were specified, and I can finish the job on the 3 by 3, and then again, then I can finish the complete job, because now I have a row completely set, and that will set the remaining rows. Am I okay? All right. I've partly convinced you by shouting, right? But that's how the proof didn't turn out to be too messy, and I probably could tighten it up a little bit in what I've described. But that's sort of the way the proof would have to argue by induction, that there has to be a row with only 1 specified. Then we check the columns. We look at the possibilities, not too many. Eventually we either rule out some of those possibilities, or we identify a smaller matrix that obeys the rules, and then by the induction step we can complete that matrix, and then we finish. Okay. So that's that. And let me tell you about, if you're willing to go 1 more minute on this question, what about completing to rank 2? Because, of course, the trouble is, another bad thing about mathematicians, once you finish, right, you get the proof. Happy. You're only happy for about 30 seconds. Because then you think of the next case. And it's always harder. So now suppose we're trying to complete a matrix to rank 2. All right, I'm jumping now to a new question. How many would I expect to specify, say in a 4 by 4? Say in a 4 by 4. How many entries would I expect to specify? Here it was 2k minus 1, 7. How many, now if I'm going to complete to rank 2, that's easier, right? Easier to rank 2, because then I can have 2 rows that are quite different, and the others have to be combinations of those. So I could have 2 rows specified completely differently. Completely, I'm using X, right, for specified. I could specify 2 rows arbitrarily. Now I could specify 2 entries in the 3rd row, and then do you see that I could finish the job and keep rank 2? What I'm trying to do first is guess the right number. And I'll do that by assuming that they're in a nice pattern and see, okay, how many could I expect to do in that pattern? Okay, suppose I'm given 2 complete rows. Then if I'm given this row and this row, that number and that number, that tells me what combination of this row and this row it takes to get these 2 guys right? I've got 2 coefficients in that combination, so I can take a combination that'll get these 2 right, and then I better have those unspecified because they're going to be whatever they come out. And similarly here, I can specify 2, and some combination of those 2 rows will match those 2, and then those unspecified ones will be filled in. I'm discovering in a 4x4 case, I would think I can specify 12. But that's the question. Here those 12 I can specify. And of course, right. So the question is, can I always?
Looks an awful lot like your 2x2 case with rank 1.
Yes, it's okay. So I went away thinking, well, all right, got this proof, got the right number here, 12, can't be that hard. But then I came up with a case that I didn't know how to do it. So I decided this is, so I don't know I don't have a proof yet. I should say we. I'm doing this with a really sharp young guy named David Ingerman. He's the source of ideas here. Okay, so now can I specify any 12? Well, let me show you what I got hung up on. Could I specify, this is 4x4, I think I can specify 12, I was pretty sure, but now suppose my unspecified are the diagonal. And I specify all 12 of these guys. So I specify those 12 numbers, and these 4 I could leave blank as a sort of way to see that those are not specified. And I want to fill this in to have rank 2. Fill complete to rank 2. Well,
can you interchange rows and columns?
The
first matrix to get it in the form of the second?
Well, if that's, yeah, if so, done. But the trouble is, there's a row with only 2 guys in it. If I move it elsewhere, it's still got only 2. If I move, yeah, but I mean, this is exactly the right question. So I move that row up or down, still has 2. If I change columns, what happens on that row? Those 2 are still there, they just in different columns. So that's why this one was so hard, because this has got 3 in every row, 3 in every column, and I can't, with just simple reordering, get out of that fix. So I couldn't see how to do it, frankly. You know, where do you start? I didn't have a starting place somehow. And let me call these numbers like A and B that we would like to be able to find. A, B, C, D. Okay. Now, yesterday afternoon, David convinced me we could do this one. So I can show you what he sold me on here. Okay, how he did it. And then that's only, so at this point, this is again a progress report. Our progress report, I think, is he figured out how to do this one, this particular one. So we still have the question of any 12 in a 4x4. And then the more general question is, so completion, so let me complete the theorem. Completion to rank 2, the number here becomes everything is 4k minus 4. That's the right number. Which when k is 4, that's 16 minus 4, which is our 12. So this is the guess, conjecture, you could say, completion to rank 2 is possible if and only if every submatrix of order k has no more than 4k minus 4. Let me check 3 by 3. What would that say? I'm saying that I can complete to rank 2, and suppose it was 3 by 3. How many am I specifying? I'm specifying 8. Now, is it true that if I had a 3 by 3 matrix and I specify 8, well, how many have I got left? Only 1 left. Can I get rank 2? That one, if we can't do 3 by 3, well, just go and shoot ourselves. So 3 by 3. 3 by 3. So this is rank 2. I'm still into the rank 2 thing. If 3 by 3 and with 8 specified, 8 x's, well, put them wherever. That's 8. Only 1 left. Only 1 freedom left. But I want to get. I'm aiming for rank 2. How do I do it?
Just the same proportion.
Yes, that's right. So in terms of linear algebra, so this is unspecified. Some combination of that. Well, a quick way to say it is make the determinant what? 0. Make the determinant 0.
Which determinant?
The 3 by 3. If the 3 by 3 determinant is 0, what's the rank? Less than 3, 2. Take 2, right.
Does that have to be exactly rank 2?
No.
Less than or equal?
Less or equal rank 2. Yeah, less or equal rank 2. Yeah. I have to achieve rank 2, but of course if I specified stuff, if I specified that row exactly in the same direction as that row, then and all sorts of stuff, then I could maybe even get lower rank. But I'm shooting here for rank 2. So I'm saying if you give me 8, I can certainly fill in that 9th. Well, one way, the way we saw it was some combination of that row and that row will make those 2 right, and it'll tell me what that has to be. And I'm just saying, to say the same thing in another language, some number there will make the determinant 0. Some number there will make the determinant 0, so I'm okay. But, so 3 by 3, completing to rank 2, no problem. But 4 by 4, with 12 specified, completing to rank 2, big headache. Okay, so can I come back to this one now? This is my last case that I know about. And then the goal is to get the theorem to work for rank 2 completion, where this is 4. Okay, here was the idea. Suppose I look at this, and this. So a 3 by 3. And I certainly have to complete that to rank 2. So what'll it take? Well, let's look at the determinant. So I'd like to complete this. So what's the determinant? I have to make the determinant 0, right? If I have a 3 by 3 and I'm trying to get lower rank 2, that surely means it's singular. Its determinant is 0. So the determinant of that will have to be 0. So what is the determinant? It's a times b times a times b times something times something. And then what else? How many? You remember a 3 by 3 determinant? What's it going to look like? It only involves, there's an AB term, and then there's an A times something, Q, A times some specified, and a B times something specified, and other constant and other specified terms that don't involve A and B. Has to be 0. That's the determinant. That's the 3 by 3 determinant. Okay, but the thing is, it involves both A and B. So, I mean, that's only one of the many equations, many 3 by 3 determinants, but it's the one I want to look at. And the other one I want to look at is this one. I'll circle another 3 by 3 that's interesting in yellow. Take this I just want to use A and B. I want to use this, this, and this. And now let me see. What? A, B, where's it gone? I haven't got David to help me here. I'm looking for, and this, is that right? I'm looking for a 3, no, here. This, this, and this. Okay. There's another 3 by 3. So its determinant also has to be 0. And it's independent because it involves these 3 numbers and not these 3 that appeared here. So for this determinant to be 0, okay, what's that determinant? Well, again, I have an AB. It looks just like this. AB times some other specified thing plus A times some other specified thing, Q, plus B times some other specified thing, R, plus some other specified thing has to be 0. Well, out of this here's the punchline then. Out of this I can determine A and B. They're nonlinear equations. That's a little scary, but I can subtract the right multiple of this equation from this one and kill the AB. And then I have a linear equation connecting A and B, so I can solve for A. Then I can plug in. Then I get a quadratic equation for A, which I can solve. It's 2 solutions, and I don't yet know whether they're both okay. And then back to find B. In other words, this leads to A and B. And a similar discussion, starting sort of symmetrically upwards, would lead to C and D. And I believe that they would then be right. I haven't even completed that part, but I think it would be. So anyway, that's a progress report. That we now have equations that determine the A, B, C, and D, and we believe that when they're determined, the whole thing will have rank 2. And then we're, I can't say off and running because I don't have a general pattern there. So it's still much to think through here. I do want to. So that's just. I just thought you might like to see 3 things about this problem. In the rank 1 case, you saw how a final theorem looks, how a proof could do the whole job, and what a proof consisted of. In this case, you see a theorem in progress, where one case is clear. We've now puzzled out another case, but in our heads we know the job is all cases, and we're not going to get all cases by exhaustion. The only way we can get it is eventually to see a pattern here, and we don't see it yet. And now, thirdly, I just want to say, because it wouldn't have happened except for this giving this course, that do you remember that I made the remark about something I had not known, that if I have a tridiagonal matrix, and let's assume these are non-zeros, so it's a tridiagonal matrix. Do you remember my remark about its inverse? Probably not. I didn't. So in the beginning of the course, we had particular numbers, 2s and -1s, and we computed the inverse. Those special matrices, K and T, and so on. We actually found the inverse. So I thought that was interesting. Then those inverses had a special form, and then I read that form is always there. And what was that form? That form was that above on and above the diagonal, so for these 12 guys, that was rank 1. So that was the thing, that the inverse of a tridiagonal matrix has low rank above the diagonal. So above the diagonal here, it's of the form ui times vj. This is the ij entry of this is t for tridiagonal. Its inverse, the ij entry, has this form ui vj. And let's suppose it's symmetric. Then it has low rank above the diagonal. It doesn't have low rank overall. So this is a different question from the completion. We were trying to complete, to have low rank for the whole matrix. Here, the thing's invertible. The rank is full. The rank is n. But half of it has low rank, and the other half has entries by symmetry. They must be uj vi, and the total rank is n. But the interesting part was that, and new to me, was that half of it had rank 1. Yeah, I jumped in a question.
Lex, in his work on noise, showed that, I'm not sure where he got it from.
Okay.
That if you take a correlation function, e to the, say, absolute value minus absolute value t.
Okay, take a correlation.
Which is like that.
All right, yes.
On the right.
Okay.
Then you get the inverse. When you do the inverse of the correlation, it comes out
As tridiagonal. Okay, so there was a specific case of importance. Right. And these cases that we did were specific cases of importance. And I had no idea that sort of this was always happened. That if you had rank 1 here, then on the other side you had tridiagonal. If you have rank 2 here above the diagonal, what do you figure? Then this one will be 5 diagonal. So I guess now I'm sort of looking for a general law there. I guess I'm not looking. So the general law is then known that if we have rank 5 here, then I mean it's a big matrix. Say rank 5 above the diagonal, completed by symmetry. So the thing will have full rank, but the other side, the inverse, will, if I said rank 5 there, then it would have 1, 2, 3, 4, 5 diagonals above the main diagonal and 5 below. Okay, fine.
What do you mean by rank above the diagonal?
Well, yeah, good question. That's what led us to this crazy stuff. What do I mean by rank above the diagonal? Well, I certainly mean that if it has the form ui vj, who asked the question? Yeah, I mean, I identify immediately a matrix. That's what I mean by having rank 1 above the diagonal. If it has a form ui vj, that means it has the form of column. That's one column of u's, u1, u2, u3, times a row of v's, v1, v2, v3. The entry in that would be ui vj, and it's a rank 1. It's a column times a row. So I recognize that as a rank 1 matrix, and I'm seeing it here in different notation. So that's what I mean by rank 1 matrix. If I completed the whole matrix by this pattern, I would have rank 1. But symmetry completes it with the opposite pattern and gives me full rank. And yeah, so that would be the rank 1 case. Yes. All right, here's my idea. Here's my idea. Okay, algebra is saying that if we have a certain number of diagonals here, we have a certain rank here. Fine. Can't beat that. Okay, now, but I think there must be behind that somehow a more general rule that if the thing is approximately a band matrix. Now, what does that mean? If it tails off fast, you see, what I want to do now is generalize this to when these are not necessarily strictly 0, and this has strict rank whatever, but I want to see, it's sort of like Heisenberg somehow. If this tails off fast, then this has pretty close to rank 1. There's my conjecture. That if these are little, then the rank here is near 1. Okay, what does that mean? I suppose it means that I have a rank 1 matrix plus something small. So there's my conjecture. Unwisely stated here and imprecisely stated, but you see that it's reasonable, right? And if it's reasonable, it's probably true. And if it's probably true, it's probably been proved. That's the bad point. But so that'd be my guess, that if I have a matrix that's almost a band matrix, then its inverse is almost a rank, almost a low rank above the diagonal. Okay, stated that way, it sounds like it's pretty clear. So I have no idea whether that idea, whether that concept will be, it may be not difficult to pin down, but it's sort of the step from algebra to analysis. It's algebra when you're talking about strict zeros and strict rank. Analysis is when you get things like near 0 and near rank. Then it's estimates of inequalities. You're bounding things, and that's sort of the difference between those two parts of mathematics. So, and most people are sort of on one side or the other. Algebraists are just have that knack of playing with combinations. And analysis is more about if you're given certain bounds on something, what bounds do those imply on other things? Okay, I've taken more than an hour on this lecture, and let's make this then. Can we take a break? I'm happy to and also, so I'm going to call this then lecture 32. Will be concentrate on game theory, and apologize for a work in progress like that, but maybe at lecture 31, when I feel I know you all so well, you forgive me for describing something that's incomplete, but connected to what we've been doing. Okay, so
Would this have some application in computational?
okay.
You're going at this very hard, and I keep wondering.
Does it have application? Why? Why? Okay. Why? All right. Fair question. Right. And what's my answer? Well, it's really, you're really seeing what a mathematician who's sort of on the border of pure and applied, what happens? I mean, yes, I do hope it has applications. And I guess in this final minute here, I was describing my coming back to applications, because a lot of matrices in applications are big on the diagonal and tail off.
I'm talking about being band limited.
Yes, that's right. Yeah, exactly. I mean, that's another word that falls into this thing. So diagonally dominant is a and people. So you meet a lot of diagonally dominant matrices that they make your life easier, and because somehow they're better matrices to deal with. They're probably positive definite because that diagonal is so tough that it makes the thing positive definite. But then you want to say why? What's the consequence in the inverse? Yeah. So maybe at this point I'm thinking of applied here, But over here, it's pure fun, right? I mean, yeah, who knows? There could be an application, but I don't require that to get excited about it. That's the reality. I just require a puzzle that I can't see the end to. Yeah. All right. Good.